Kia ora, Year 12 and 13. This is the first part of question 3 from the 2015 Scholarship Calc paper. So I think this is probably worth about 2 marks out of 8, but it's actually a really nice little warm-up question. The trick here is not to go down an enormous rabbit hole on the first part of this question, because this is a very, very easy little proof if you see what to do. Okay, so to have a look at the question and just jot down 2 bits of level 3 calculus that you're going to use to do this. So do that now. Alright, so hopefully you jotted down de Moivre's theorem, which I'll just call DMT. And this one here, if we've got something to the power of 6, we might spot a few familiar looking numbers and coefficients in there. This is going to be something to do with some kind of binomial expansion. Okay, so we haven't spent much time on that this year, but if you look in chapter 27 of Delta, of the old Delta, there's some fantastic stuff in there. Now, we did it really, really early in the year, so most of you have probably forgotten about it. Okay, so the first part, we want to prove that if z is equal to cos theta plus I sine theta, which we'll just shorten to cis of theta, then z to the power of n plus 1 over z to the power of n is equal to this. So we can start by writing this as z to the power of n plus z to the power of negative n. Now we know by de Moivre's theorem that z to the power of n is equal to cis theta to the power of n. So I've got an r of 1 in there, that's nice. So this is just equal to cis of n theta. So that's all good. The thing you want to remember here is that you can do that whether you've got positive or negative powers. Okay, and we don't do that much in level 3, but it all works fine. The proof just follows through. And that means that z to the power of negative n is equal to cis of negative n theta. Okay, I'm going to take a new slide to finish off this question. So z to the power of n plus 1 over z to the n is equal to cis n theta plus cis negative n theta. Now I'm going to expand it out and get the real part and the imaginary part. So I've got cos of n theta plus I sine of n theta plus cos of negative n theta plus I sine of negative n theta. Right, cos of x is equal to cos of negative x. Cos is an even function. And sine of x is equal to, sine of negative x is equal to negative sine of x. Right, because sine is what we call an odd function. Now that should be really deeply ingrained in your brains by now, because that often comes in handy with harder trig problems. Just think about the graphs of the two functions if you've forgotten that. Right, so now we can simplify that, but we need to write down something like that, or cos is odd. Cos is even and sine is odd, just to show what we're doing. And down here, we're going to get 2 cos of n theta, because this one here is the same as that, plus I sine of n theta minus I sine of n theta, because it's an odd function. So we've got there, except I've run out of space, but that won't happen to you. So the final step is equal to 2 cos of n theta as required. So that's the first bit done. So that's probably 1 mark. You only need to get to 20 something. Right, on to the next part where we're going to use this result. Now, let's look at what we want to show first, as usual. So we want to show that cos of theta to the power of 6 is equal to 1 over 32 cos of 6 theta plus 6 cos of 4 theta plus 15 cos of 2 theta plus 10. So you can sit and stare at that for a minute, and then you can say, well, we're meant to be using this result here, that z to the power of n plus z 1 over z to the power of n is equal to 2 cos n theta. If scholarship examiners have given you a hint, it's really going to be sensible to use it, right? Because it will always make the problem not that bad at all. So if you look at that, then you go back up here and you look at this and you go, well, I can't really see anything in here. we want to be working with a cos of theta to the power of 6. So let's just play around with putting n equals 1, and we'll see what happens. Well, then we get z plus 1 over z. I don't know why I've put brackets in there, or there. It was a bit silly. Right, z plus 1 over z is equal to 2 cos of theta. So I still can't see a cos theta to the power of 6, but now if I just take both sides of that equation and raise them to the power of 6, this is what we're going to get. On this side we're going to have z plus 1 over z to the power of 6 equals 64 cos theta to the power of 6. And at this stage you should be a little bit excited because, well, maybe not. You've got a 64 here and you've got a 1 over 32 here, so you can see something going on. So the obvious thing to do here, which is the smart thing to do, is to expand that out. So we're going to do that on the next slide. We're going to use Pascal's triangle to do that in this video, but you could use it using the binomial theorem and the coefficients. That's especially if you're watching this from another school and you've done Cambridge, you're going to find binomial expansions really, really easy. Okay, so we've got, let's just look at this side. This to the power of 6 is going to give me, well, my coefficients, when I'm expanding that out, are going to come out of the 6th row of Pascal's triangle. So we're really quickly jotting those down. 6 is probably about my limit of where I do Pascal's triangle, and not just go to the combinations. Okay, but you can do either. So here it's going to be 1 times this first bit to the power of 6, and then none of those, plus next coefficient 6 times z to the power of 5 times 1 over z, and that's to the power of 1. Remember, we're grabbing 5 of those and 1 of those. Right. Next, 15 times z to the power of 4, 1 over z squared, plus 20 z cubed times 1 over z cubed. And you can start to see that a whole lot of stuff is going to collect up. Z squared, 1 over z to the 4, plus, where am I up to, 6 z times 1 over z to the 5, plus, we're now 1 times, 1 over z to the power of 6. If we squeeze onto the slide, what we get when we collect that up, and then most of you can probably go from here. So there's z to the power of 6 there, plus, well, here I've got 6 z to the power of 4, and looking through, that's going to be all I've got there. So 6z to the power of 4. Now this one here, 15z squared. Oh yeah, actually stuff doesn't go out here at this stage. Right, so plus 20 plus 15 times 1 over z squared. So you should be seeing patterns, right? So one of the reasons you'll be doing scholarship calculus is because you'll be really good at spotting cool patterns, and here's one in here. Now, think back to what we're going to use to help with this problem, and it was the first result where we had only the new slide. So we had z to the n plus 1 over z to the n is equal to 2 cos n theta. So we're going to use this now, because what we've got is, where did we get to? Well, we had 64 cos to the power of 6 theta is equal to that left-hand side. So we're going to group them like this now. Z to the 6th plus 1 over z to the 6th plus z to the 4 plus 1 over z to the 4, and there were 6 of those, so times 6 plus 15 z squared plus 1 over z squared plus 20. So notice we lost all of our powers. So applying this, I'm going to get 64 cos to the power of 6 theta is equal to, well, here, this will be 2 cos of 6 theta. Next one will be 6 times 2 cos of 4 theta. The next one will be 15 times 2 cos of 2 theta plus 20. Okay, one last slide. You probably don't need to watch the last bit. So 64 cos theta to the power of 6 is equal to what? Well, we've got, where did I get to? 2 cos 6 theta plus 12 cos 4 theta plus, sorry about the music in the background. It's one of my kids doing their violin practice. I hope you're enjoying it. So now we're going to divide through both sides by 64. Might as well go straight to that. And we get cos theta to the power of 6 is equal to 1 over 32. Where are we? Cos of 6 theta plus 6 cos of 4 theta plus 15 cos of 2 theta plus 10. So I could have done another line there, but I'm not really sound my own voice at this point. I'm just dividing through everything by 2 here, right? Okay, so there you go. Now, the last thing I'm going to show you is the rabbit hole I want you to avoid, which is in the first part of the question, if you don't spot de Moivre's theorem applying to negative numbers. Right, so we had to prove, way back at the start, that this was equal to 2 cos n theta. Now, I'm pretty sure that anyone sitting scholarship is going to spot that the way to start this, by this stage in the year, is to use de Moivre's theorem, right? But some of you might not have seen that z to the negative n is equal to cis of negative n theta. Okay, so suppose we can do that. Let's look at what would happen, because you're still going to get there. And for some of you, that's going to be absolutely great, because you're still going to get one tick, and you'll be looking at every tick you can get. But I just want to show you how much it's going to slow you down with what should be a pretty quick start to question 3. So if we then go ahead and just substitute in, here's what we're going to get. We're going to get cis n theta plus 1 over cis n theta. So that's if we didn't see this. Suppose we hadn't seen that. So this equals cos n theta plus I sine n theta plus 1 over da 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 da. Right, and then if we get a common denominator, down here we're going to have cos of n theta plus I sine of n theta. And up here we're going to have cos of n theta plus I sine of n theta squared plus 1. So I guess what I'm saying here is it's a totally fine way to go, and you are going to get to the, you're going to have a nice proof coming out, but you're going to take about another 10 lines to get there, and that's going to waste time. So you want to have done, I guess, enough exercises that you're spotting all of the connections that you need to make so that you can get to the heart of the problem as efficiently as possible. Alright, so if you want to talk to me about how to do this the long, clunky way, feel free to do that in class. Okay, thanks for watching, and let me know if there are any mistakes.